It powers literally everything. Our homes, our phones, our entire modern world. And yet, it's completely invisible. So today, we're going to pull back the curtain on this amazing force and break down exactly how electricity actually works.
I mean, it seems so simple, right? You just flip a switch and the light comes on. But behind that one tiny action, there's this whole fascinating chain of events, all governed by the laws of physics. So, what is the real story behind flipping that switch?
Okay, so to get to the bottom of this, we have to start with a thing that's actually, well, flowing. It all begins with a fundamental property of matter called electric charge.
And this right here, this is the absolute core of our topic. Just think of electric charge as this tiny, built-in property that particles like electrons and protons have. It's the most basic ingredient. Seriously, without charge, you get no electricity, period.
And these charges, they follow some pretty simple rules. You can almost think of them like tiny magnets. Positives push away other positives, and negatives push away other negatives. But put a positive and a negative near each other, they pull together, they attract. And that simple rule, opposites attract, likes repel, is basically the engine that drives everything we're about to talk about.
And just to give you a sense of the scale we're talking about, look at that number. That's the charge of one single electron, measured in something called coulombs. It's an unbelievably small number. That means trillions upon trillions of electrons have to get moving all at once just to power something as simple as a light bulb. It's wild.
All right, so we've got these charged particles, but they're not much good to us just sitting around. We need to get them moving, and not just randomly, but in an organized way. We need to create a flow.
And that organized flow of charge, that's what we call electric current. You've probably heard the term amps, right? Well, that's all it is. A measure of how many of these little charges are zipping past a certain point every single second. This is the flow part of our story.
But what makes them flow in the first place? Here's a great way to think about it. Imagine you've got 2 buckets of water connected by a pipe. If the water level is the same in both, what happens? Nothing. The water just sits there. But if you raise one bucket higher than the other, suddenly the water flows from high to low. That difference in height creates pressure.
Well, in electricity, that pressure has a name, potential difference, but you and I know it better as voltage. A battery or the outlet in your wall is creating that electrical pressure, pushing the charges from a point of high potential to a point of low potential. And here's the crucial takeaway. No voltage, no flow. It's that simple.
Now, it would be great if these charges could just cruise along a perfect superhighway with no problems, but that's just not how the real world works. There's always something getting in the way. There's always an obstacle in the path.
And that obstacle, that friction, is what we call resistance. As those little electrons try to move through a wire, they're constantly bumping into all the atoms that make up the wire. It's kind of like trying to run through a really crowded hallway. This creates a sort of electrical friction that slows the whole flow down.
Okay, so let's put these 3 big ideas together. It's a really simple sequence. First, you need the push. That's the voltage. That push gets things moving, creating the flow. That's the current. And finally, that flow is always getting slowed down by the friction, and that's the resistance. Push, flow, friction. That's the golden rule of circuits. V, I, and R.
And this whole relationship is wrapped up perfectly in one of the most famous and useful equations in all of physics, Ohm's law. V equals I times R. It's so elegant, so simple. And this little formula? It is the mathematical backbone of pretty much every electronic circuit ever designed.
All right, so we've met our 3 main characters, voltage, current, and resistance. But now we need to talk about the stage they're on. Because how you arrange things in a circuit, the actual path the current has to take, is just as important as the players themselves.
First up, you've got what are called series circuits. Just think of it as a single file line. Everything is connected end to end, one after the other. This means the current has only one single path it can take. But there's a huge weakness here. If any one part of that chain breaks, the whole thing goes dead. You know those old cheap holiday lights where one bulb goes out and the entire string dies? Yep, that's a series circuit.
The much smarter alternative is a parallel circuit. Instead of one path, the current has multiple roads it can travel down. It's like a highway with multiple lanes. The current splits up to go down each path. And here's the best part. If one of those paths gets blocked or breaks, the others just keep on flowing. The rest of the circuit stays on.
And guess what? This is exactly how your house is wired.
It's basically one giant parallel circuit. And thank goodness for that. It's the reason why when one light bulb burns out in the kitchen, your TV in the living room doesn't suddenly shut off. Each appliance is on its own independent path, making the whole system practical and reliable.
Okay, we've gone through a lot of the theory, the push, the flow, the pass. But so what? What does all this flowing and resisting actually do for us in the real world? Let's talk about the results, the things you can actually see and feel.
The first big effect is power. We measure electric power in watts. And all that really means is how fast is energy being used? It's a rate. So a 100-watt light bulb is just burning through energy twice as fast as a 50-watt bulb. It's as simple as that.
Now remember that electrical friction we called resistance? Well, what happens when you rub your hands together? They get warm, right? Friction creates heat. It's the exact same idea here. As all those electrons bump into atoms inside the wire, they create heat. It's just an unavoidable side effect of moving electricity around.
And this heat can be a good thing or a bad thing, a friend or a foe. I mean, we want our toaster to get hot, right? That's its whole job. Same with an electric heater. But we definitely do not want our laptop or our phone charger to get super hot. So it really just depends on whether that heat is doing useful work or if it's just wasted, unwanted energy.
So, when your electricity bill shows up at the end of the month, what are you actually paying for? You're not paying for voltage, you're not paying for current, you are paying for the total amount of energy you used over that month. And the special unit they use to measure that is the kilowatt hour.
So what on earth is a kilowatt hour? Don't let the name scare you. It's really just a big bundle of energy. To be specific, one single kilowatt hour is equal to 3.6 million joules of energy. And that is the unit, that's the currency that the power company uses to figure out how much to charge you. And that brings us to our final thought for today. Now that you understand the push, the flow, the friction, and the power, I want you to take a look around, wherever you are right now. Based on everything we've just talked about, what do you think is the single biggest energy consumer in your home at this very moment? The answer? Well, it just might surprise you.